Hello. This is going to be something of a secret stream. Last week I accidentally told chat that I wasn't going to be here this week, so I'm not expecting chat to be here because I told them that I couldn't do this weekend. But secretly, I am available this weekend. I am here and I'm streaming. So I'm going to very quietly, okay, Mary, say hi, Mary. But I'm going to very quietly get on with some maths. It occurs to me now I could have just taken the afternoon off and done something different, but here we are. I'd probably be doing maths anyway, so I might as well do it on Twitch. Right, how are you doing, Mary? You all right? Anybody else? Twitch says I've got several viewers, which suggests that I'm not that good at dissuading people from checking in at 2 o'clock on a Sunday. Hey. I do normally, if I'm actually going to cancel a stream, I do normally remember to hit the button. There's a button in the Twitch dashboard that lets me, I think, display it as cancelled. I normally remember, but sometimes I tell people I'm doing all right. Thanks. Thanks for asking. Yeah, having a nice quiet weekend, and the weather's just got really good. It's so sunny outside. It's lovely. Hello, Herb, as well. Right, yeah, it didn't work. It wasn't supposed to be a trick. Just at the end of last week, I said it the wrong way around. Right. Welcome back, people. We've got on screen at the moment a version of this thing called the fairy diagram, and it's the version I like thinking about at the moment, I think. I'm considering trying to remake part of it in Desmos so that we can have a kind of zoomable version that zooms in. I'm not certain how I'm going to do that. I am a bit aware that as soon as I say Desmos version of this, there's a chance that someone in chat might just make it in Desmos before I've even started. So I'm taking that risk that, it's my secret stream. Okay. The challenge here is going to be something like, the challenge here is going to be something like drawing infinitely many circles or drawing lots of circles. There's a sort of iterative process here, but the process as I'm currently thinking of it, if you just look between 0 and 1, draws this kind of M shape, and then on the next iteration draws 2 M's, and then sort of draws twice as much M's each time. I might be trying to recreate this in Desmos, so I can zoom in and look at, for example, zooming in on root 2 to see the the convergence on the way in. I think a zoomable version might be fun. On the other hand, maybe no version of this can possibly do it justice to have all of the very many bits that are going in here. So I think this point, it's already connected to 1 and 1/2 and 1/3, and I think that's a 1/4 and 1/5. It's supposed to be connected to all of the 1/n's. So maybe no version of this picture can do it justice. Although I suppose those semicircles will be quite small in both directions as you go towards 0. So maybe it'll be all right. They're all contained within each other, so it's kind of a limited region where there's lots of semicircles, which is, I suppose, the nature of this game. That something we learnt last week, which is rather brilliant, is that if you keep doing this, putting in these are called the medians. So anytime you have a semicircle, you draw in 2 more semicircles inside, where the point where you arch both of your semicircles into, that point follows something called the median rule. You look at the previous fractions and you just add the numerators and add the denominators. So it's not adding fractions. So 0 plus 1 is 1, and 1 plus 2 is 3. Welcome to John Maths. So this is the 1/3 has been added in. That's the logic for drawing just this arc coming in here and that one coming out. Those are inspired by splitting up 0 over 1, 1 over 2, put something in the middle and join it with 2 semicircles. I kind of want to do that iteratively. I'm not great at iterative stuff in Desmos. Possibly I want to create a big list of these fractions. I'm going to try and think it through first before I do. I might not do anything in Desmos, who knows. There's this sequence. This is stuff about the median property, and we did some stuff with matrices, trying to prove that it reaches all the fractions. Is this thing where it's a series? So you do it in a hierarchy. So first you write in 1/2, and then you put in these fractions 1/3 and 2/3, and then you keep going. Hey, famished. How's it going? I'm good. I'm doing a secret stream because I accidentally told people it wasn't a stream, and then it was. So I don't know why, for people in chat who have loyally turned up even on a Sunday afternoon, but hey, even more chill than normal. It's a stream that maybe wasn't going to happen and then did. Something I've noticed is that primes. No, what am I thinking? Something with primes. Yeah, you can't just go. So at this point where we've got to the prime 7, have we got everything with a lower denominator? Yes, of course we have, because we've built up the denominators. The reason we're missing some things, like 2/4, is just that they're not in lowest terms, because we already have them. So I think I need to work out, there's a rule, by the way, about looking at the determinant of the matrix. If you imagine that the fractions are actually vectors, and you put those vectors into a matrix, then the determinant of that matrix is supposed to be 1 or -1 if they're connected with a line. So maybe we could do something like that to just sort of look at all possible fractions with a condition. I know I can do conditions in Desmos based on regions of space, like X and Y. But if I have lists A, B, C, and D, can I plot points? Yeah, maybe that's the first test. So I made this, like this, so you can zoom in on route 2. But this is very finite. I listed some convergence for route 2, and I'm visualizing them, and I got bored. Why is that stopped there? Because I didn't update this to be quite the right number of things. Oh, still off. It's in here somewhere. There we go. No. I don't know anymore. Oh no, I've now joined up to the last dot that I could be bothered to put in this list. This sort of thing. I like the zooming. The ones in the textbook don't let me infinitely zoom. Probably the one in Desmos is not going to let me infinitely zoom either, but it might let me zoom a bit. So I think the test that I want to do, test rather than loading my emails, good lord. The test is something like, oh, I should be really careful with this, shouldn't I? The test is something like, if I have some lists of numbers, 6, 7, 8, can I do logic based on those lists? So for example, if I want to plot the points AD, which has got some relationship, but can I do that such that B is less than 7? Will that be logic? Yes, it will. Ooh, okay. Okay, so I can filter on that logic. So why is that not happy? So I'd like it if that's a thing. That's a number. Maybe this thing is never positive. Yes, it's always negative for those, for the things I've got. But if I had a list of numbers, yeah, so I need a grid. We've got methods for making a grid for all the fractions, and actually I want all possible pairs of fractions, and then filter them down to just be the ones where AD minus BC is 1. Probably I should think about actual better ways of generating this group rather than just taking all possible. I'm sort of in some sense here being lazy and just taking all possible matrices. And only looking at the ones that meet the criteria I want. That is super lazy. We're going to hit the list limit quite quickly as well. If I'm stupid about this, right? So I think the limit is something like 10 to the 4. Yeah, 10 to the 4 is the list limit. So I can only go to denominator 10 if I do this in a really silly way by letting A, B, C and D range and then doing the kind of quadruple for loop to look at all possibilities filtered down to AD minus BC equals 1. Okay, but that's intriguing. That gives me a way that maybe I could start to think about these things. Yeah, it's not a property of the fraction, it's a property of the pairs of fractions. So I sort of want to, connect the fractions if they have something going on. That is going to be really hard to do as a quadruple for loop, just because Desmos doesn't really do quadruple for loops, for loops nested together. It probably shouldn't. Does it do list comprehension? That would be easier. I can't quite remember if it does list comprehension. I think it probably does. So something like, yeah, it does. I can't remember the syntax for this. It's something like that, isn't it? Yeah, it's something like this. But I want to put multiple fours in it. Because I kind of I've learned to do this in Python at some point, right? Okay, not happy. Right, okay. So I was optimistically hoping that I could do it like this. Maybe I need to, is that going to now nest everything together? Yeah, I can't store a list of points like that. Oh, just a comma in between. Thank you, Maths222. If I want my second. Perfect, look at that, there's a square. Brilliant. And what I'm actually considering is the frankly ridiculous A, B, C, D, which is 4-dimensional, but whatever. Oh, points may only have, okay. Can you list them? Points may only have 2 coordinates, disaster. Points may only have 2 coordinates. But that's all right, I can just, let's do for now a A over B, comma C over D, which is not quite the point that I want. For A equals 1. This is pretty daft. A, B, and I want C to range from 1 to 3 as well, and D to range from 1 to, for now, 3. Okay, so this has got some fractions, and it's formed a rather nice chart of fractions. Oh, I quite like that. Okay, but I actually want to do some restriction on this to say that I want AB minus BC to be 1, and that's found none of them. It wants me to add sliders. Because can I have like an if or something? Or where? Or condition this so that instead of just looping over these. Right, so a second ago, before I deleted it, I had them as vectors, and then it could run the logic on those vectors, but doing it as list comprehension, maybe I can't. Is there like a such that? Or if, or where, or provided that. With? Really? Yeah, it is with. Oh my goodness, well done. It's not happy with me. Maybe I have a comma in here or something. No. With's definitely a keyword. It's gone. Hi, Charlie. We're doing mean things to Desmos by forcing it to think about fractions. Curly braces around it, maybe? I'd quite like 1 instead of. So it's now just cross with me, right? Quick check. So maybe this is problematic somewhere. So A, comma A plus 1 with A less than 2. Yeah, not keen on this. Charlie got to Cambridge. RFL. That's what you want. Very nice. Very good. Just step to go, I guess. Unless I think you're the math sort of thing. Maths, that worked. Well done, Charlie. There we go. Good job. We've now got some fractions. We've got a list. It's pretty silly, but I think we've got a list. We've got some points. Can I give it a name? I'm going to put P for points. We've got 81 of them because I think we've got repeats somehow. Oh no, that's all of them. But we're only plotting these ones. Ooh. Ooh. Oh, you want to step live stream? Oh yeah, we can do step live stream now if you like, but I got the graphics for it anytime. Previously, you've come in here and said you don't want the step stream because it's got too much other stuff, other step. I want to talk about step question actually at some point. I've got content. Might be some step. Right. The graphics don't quite line up. Everything moves when I change because I've shuffled my graphics around very slightly. It's been pretty bad. So this is annoying me that this length is still 81, which means that if I did something like plotting the points P. Oh no, but it's now. Why is it length 81? It really is suppressed. So this is somehow correctly suppressing them, which I'm pretty sure is good. So it's a list of points or something. So you do 1 to 40, like the first half of them. Oh, I keep forgetting that's not how you do lists in Desmos. You get like the first half of them. You plot some of them. Whee! Oh, it finds them in this order. That's fun. So what do I actually want then? I want to take the components because I want to do maths to these. Yeah, so I want to do, for example, I want to find the midpoints. So it's my list of like points, but I don't really want to plot the points. I want those to be real numbers. And what I really want is like my midpoints of circles, which is the average of these things. That's a big list. And I want the radii of these circles, which is that much, maybe, or possibly, not sure, like that much. I'm going to square it, it's fine. And then I actually want to show some circles. This might just do it, by the way. This might be it. That's some circles, isn't it? Here's some circles. Let's just do the upper half plane. What have we made? What have we made? Oh, we've discovered the integers. So we've discovered the integers. That's fun. So they're fractions of the form. Yeah, okay, they're good. I don't love that we've joined 2 and 4 because 2 over 1. What's happened there? So we've got 2 over 1 and 4 over 1, which I think would not work out. Why 2 and 2? Has it in fact just joined everything? Has it made every fraction without restriction? Quick experiment to see if my... Oh no, okay, so that would connect loads of stuff if I let it do that. But if I have this, maybe this is good. Between 1 and 2, it's correctly found 1 over 1, 2 over 1 works just about. And it's correctly found that the median of those things, or something they should be connected to, is 1 over 1, 2 over 1, 3 over 2. No, but what's it joined it to? What's this? 4 over 3. So why is it connected? Why have we connected 1 over 0 to 4 over 3? Because that has the correct, that does have the correct determinant. Am I just being silly? I've got a step question, because we bumped into a step question last week. Why is it not? Okay, so we've now got loads of semicircles, but somehow I've got some of the maths wrong instead, which is always fun. Oh, divide by 2. Divide by 2. Divide by 2. Circle geometry. Circle geometry. Better. There we go. Okay, yeah, much better. 1, 2, now joined to the median correctly. 1 joins 1/2, what I wanted. 1/2, and in the middle here, 1/2, 1. 2 over 3 is correct for the median in between. It's compared to here. Oh no, not this page. That was me trying to draw the circle between 2 points, but I didn't notice that it was drawing it through between the wrong points because it was doing so many at once. This is, by the way, this bit over here. We've got this bit of semicircle, and we've got this bump inside. In Desmos, I think working. So this is pretty good. What do I think? Next. So I kind of want to just push the number n. I don't need this point p anymore. So at the moment the numerators and denominators only go up to 3. I think I can push that to 10. Let's do that. What am I going to call this? So this is like the kind of maximum quotient or maximum number in a fraction, which we're going to set to be 10. And then we're just going to stick this quantity is going to be here and here and here and here, and that's okay at the moment. And it's going to be here and here and here and here, I think. Now we've generated quite a lot of fractions, and we've drawn quite a lot of circles, and this just did something pretty scary, like a kind of loading spiral. But this is looking a bit better. So, are they crossing each other? They shouldn't be crossing each other. They're not crossing each other. Perfect. We've got a bit of that hierarchy stuff. We're discovering them in a weird order. So there's loads, because we've got the reciprocals of everything as well. So we've got loads of things larger than 1, which we're connecting up, which we don't necessarily need. I'd be okay if all of these fractions were smaller than 1. If I just drew this bit between 0 and 1, that'd be all right with me. Can I set this to have B starting at A and going up to Q max? No, nonsense. That's a shame. I kind of want to do my nested for loops to do different things. If I just put a filter in here to say B greater than A, well, it's still a 10,000 element list as far as Desmos is concerned. So, that hasn't even changed. Oh dear. Oh dear. I'm sorry, Desmos. What's it drawing? I thought that would filter it more. What's it done? Or maybe that was always there and it's just been loading slowly. Okay, I can't explain that behaviour. I thought it would be more restrictive. Get in a separate bracket. Oh, there we go, separate brackets. So this is just the bit in here. I guess B could be equal to A, that would be alright. Does that join up to 1? Yay. I guess these A, the numbers upstairs could go from 0. But that's going to annoy me. But now this list is going to be too long, I think. Oops, I like breaking this one. Yeah, so these lists are too long, so I think that's 9. And now it's drawing a bit more, and a bit more symmetrically. Oh. Yeah, okay, this is a bit better. There we go. So we've got semicircles between 0 and 1. And then a median, and then the median of 0 at that point. And we've got some hierarchy coming down inside here, including some nested sublayers around there, which is pretty good. Good. And apparently this is an 81,000 element list because I'm not doing this very sensibly. We're pushing the limits of Desmos, even though I only want to draw some tiny proportion of the fractions I'm considering inefficient code. That's what I said. What's the proper way to do this? Let's try and save this. I'm going to switch back to that while I save, because I need to log in. So always save your work. I suppose the correct way to do this is probably something exciting with matrices. I don't really know if Desmos does matrices. I think it sort of doesn't. How would this work? Oh no, does it do something like this? I don't think it likes this, does it? No, it can't do lists of lists. It doesn't have like some sort of like semicolon for... No, it's really unhappy about that sort of thing. Ah, right, I read your mind. There we go. Remember to save. We have a clip highlight of the time we did not save, but that was quite a heavy Desmos application and it all fell apart. Okay, so I have my dream of some semicircles. I do not have my dream of being able to zoom because, well, you can currently see all of them. If you're watching this on some sort of tiny phone screen, then I guess I can help you out by zooming on the smallest bits of this diagram, but they're not that small. And Desmos does not enjoy rendering this. So I kind of want more. I want a way to generate only these ones, which we sort of have seen. We have sort of seen this. We think that matrices with determinant 1 or -1 are generated by multiplying together either 1101 or 1011. To take products of those. Arbitrary products of those matrices, I think, generate all matrices with determinant 1 or -1. I think that's what we've been doing. Probably determinant 1, how I've said it, and I probably actually mean 0 on the diagonal top left. Yeah, I mean 0 on the diagonal top left, or bottom right. One of those or the other. There's some matrices in here somewhere, right? There's the matrices I'm trying to remember. It's kind of matrix way where you do essentially to show that this thing on the left could be made out of basic matrices like the ones I've been not quite saying correctly, which is this one or its transpose. Both of those have determinant 1 though, so I'm confused. Never mind. You can right. There's maybe some minus signs right down here. Whatever. You can do a kind of Euclidean algorithm thing to reduce this down, which works because there's some co-prime numbers involved, and running Euclid is about doing repeated differences, and it just sort of ends up working. So it's kind of the central mystery, I think, the relationship between Euclid's algorithm, some matrices you can generate, some things with determinant 1, the Ferri diagram is all kind of the same thing in different ways. Okay. That doesn't really help me, does it? So if I had a list of matrices, I could consider multiplying all of them by this, which would generate some more matrices. It's kind of a branching process. I could take any product and then multiply it. So it's like building continued fractions. Because we saw later on that continued fractions build this fraction P over Q out of these matrices. So much later on, oh my goodness, much later on, we would think about continued fractions, and we thought about paths in the Ferri diagram, this pinball path thing, and we had big product. Where's my arm up here? We had a big product of matrices. There they are again. These ones. Yeah. So the first one's different, and then it's got 0 up here, and it's all okay. So actually, maybe I only need these. What's going on with these? Is this something simple to the power of n? No. Yes, no. Welcome back. It's multiplying small matrices. What is this squared? Sorry, it's kind of a stupid question. Oh, nothing that I was expecting at all. What was I expecting? What's going on here? Yeah, I thought that'd be easy. That's actually weird. So I thought this was a shorthand for doing the same thing lots of times, and I thought this was the thing. But it's not quite like that. Yeah, in my head this was like apply the median rule A times. What's going on up here? That's what we're doing. We're applying the median rule A times. You're telling me that's not the same thing as doing it once, A times. Lots of the same thing, all the time. Desmos doesn't have... does Desmos do Control S? I don't know. Maybe my Desmos would be improved if I practiced in Control S. I know you get this save button up here, but can I also Control S? Oh yeah, you can. Good, right. Lesson learned, you can just hit Control S in Desmos. That'll help. I really thought these were powers of repeatedly doing the same operation lots of times, where the operation was this. Am I just multiplying matrices wrong? Would be good, wouldn't it? No, I think I'm multiplying matrices correctly, the worst case. The median rule is being applied AI times. Yeah, so it's given us this. But that's totally different to applying the median rule. Applying the median rule once would be that with a 1 down there. And applying it again. What happens if I do it again? So I'll add them, right? Oh, maybe I want to do it on the right, or do I want to do it? It should be the same because that's the square. Powers are commutative. Hooray! Add the columns together. 1, 2, add 1 and twice that is 2. No, I really don't know what's going on. Oh no, these are the Fibonacci numbers. I think I'm generating the continued fraction 1 plus 1 over 1 plus 1 over 1 plus 1 over 1, which I didn't really want to do because I think I'm just calculating this continued fraction with 1s downstairs, which is 1s for the numbers appearing in the continued fraction, which is not really what I wanted to do. Hello chat, what am I doing? What do I want to do? Good to see you, by the way, Sensation Black. Don't think I said hello. Hello. Don't know what I'm doing. I thought this was a power, but it's not a power. So that kind of scuppers my idea about just generating these by doing powers of the same matrix, but I still think that's sort of what is going on. So I sort of... There's a step where you do lots of adding. So what do? You have P over Q for the tail, and you add an integer, which means adding Q lots upstairs. And there's separately, once you've done that, you turn the whole thing upside down. So it's the product of... Let's turn it upside down. Turn it upside down is like this, right? Because that takes PQ and returns QP. So it's this, but also add the denominator to the numerator so many times. So adding the denominator to the numerator means you do the numerator you already had plus a lots of the numerator, the denominator, because when you do this to PQ you get P plus AQ over Q. Again, reading vectors like fractions. I'm imagining applying this to the fraction P over Q, written like a vector here. And so I'll get P plus AQ upstairs by matrix multiplication rules, and Q downstairs, which is a bit like adding the integer A. If fractions and vectors are the same thing, then adding an integer is a bit like this matrix. And then this one flips upside down, which is the iterative steps. That's what's happening when you do. Okay, so that's the kind of iteration. So, okay. Is this one a nice power? Yes, it is. This one is 1, 1. This one is this. So if A is a whole number, then it's just a power of this simple matrix. Right, this one does nice power. This is the kind of famous kind of skew distortion one that has a repeated eigenvalue, and it's the eigenspace associated with that eigenvalue has a lower dimension than you might expect. I love this matrix, 1, 1, 0, 1. So if I do powers of this one, I get back to that. So that's the thing that's like repeatedly doing stuff. Oh, okay. So this is not just powers of the same thing, because that would just give me a big power. It's powers of this matrix separated by that matrix. Right, which is the group. It's the same thing as saying the group generated by these two matrices, because that one's got order 2. So seeing 2 of these in a row would be rubbish. But this one has, infinite order, or whatever you say. So you can have long chains of this one interspersed with just one of those. Those are the words in the group generated by these two matrices. And now we're getting somewhere, because now we can do all continued fractions. Still a hard problem where you've got to take. So it specifies the things that I want to draw. Because they're secretly continued fractions, I have to draw every sequence of integers. It's quite a lot of sequences of integers. But teaching Desmos how to iterate through sequences of integers, how on earth am I going to do that? I sort of want it to evaluate from the, I wanted to evaluate from the left. I get, oh look, so then at the end there's one of these, which might be there. Well, A0 might be 0, so it might be the identity, and that's also a power of these. So we kind of have like a chain of beads where you never see 2 black beads in a row. You can have any number of white beads. That just gives you a more interesting matrix. But there's never any point in having 2 black beads together because they have order 2, so they would cancel. So you can consider sequences like this of beads that are finite in length. Goodness knows how to get Desmos to iterate over those. This be easier in Python. I should just do this in Python. I'm not going to do it in Python, don't worry. Right, okay. Good. What is going on? It's 2:30. We've done some silly things in Desmos and thought a little bit about generating matrices of a particular format. That's a good start. I think I want to go back and look at forward circles because I skipped them the first time through, and I think they're about to become relevant or interesting. It's a section of this textbook that we're looking at. And by the way, if you want to play along at home, there's a link to just get this textbook online for free. It's Hatcher's Topology of Numbers. Hatcher has, in a cool manner, made it available online for free. You can also buy a physical copy if you want to. Thank you, Hatcher. It's a good book. It's got a very good introduction, but if nothing else, tells you how to find all of the Pythagorean triples. So if you've always wondered what the Pythagorean triples are, or how to list all of them, then that's chapter 0. Right, okay, so here's this thing with circles that are tangent to each other. Yeah, and this is somehow the same picture. All the points of tangency are the same as in the fairy diagram with the semicircles. And it's because of maths that I'm now going to try and understand. Off we go then. So there's a big line of circles of equal radius, and then somebody is filling in smaller circles into the gaps. and this is secretly going to be the same sort of determinant fact. So somehow this is going to specify, if you know the location of this point of tangency and this point of tangency, then you know, well, maybe you don't know everything. Maybe you do. Maybe there's a relationship between the radius of the circle. I can imagine various circles that are tangent to each other and those 2 points of tangency. So there's something else going on. Okay, good. Let's solve that mystery. I suppose, hang on, if you know the radius... Maybe there's going to have to be a relationship between the radius and the place where the point is. Right. What is going on here then? If we connect the centres, pattern of triangles, right, we saw some pattern of triangles. The vertices of these triangles, okay. The circle whose centre is labelled A over B, I wasn't paying attention, is tangent to the x-axis at exactly the point A over B on the x-axis. That's quite nice. So, for an edge of the Fairy diagram with endpoints labelled A over B and C over D, draw 2 circles tangent to each other and tangent to the x-axis. I can imagine lots of the ways to do this, but the radius R and S. Yep, not uniquely determined. There you go, at the bottom of the page. In fact, choose R and this determines S. Yes, anything works. Any positive number for R. We find a formula for how they're related. That's true. I'm sort of hoping that the relationship also depends. It feels like the relationship matters because it'll help inform me about where this kind of hypothetical next circle is. That feels like it depends on the big circles, but I suppose it's not obvious that it does. No, I've thought about it a bit more. It is obvious that it does. If R is huge, then this circle is enormous. Radius S has to be tiny, and then the next circle has to be nearby. Ooh, wobbly argument. If they're equal, then it's in the middle, so it feels like it matters. Yeah, okay. Here's some condition. Maths. Am I going to read the maths? Maybe I'll read the maths on a second time through. Okay, maths for some relationship in R and S. Oh, it's pretty nice. It's just that the product is determined by what those numbers are. And now they're going to say if those things. Yep, okay. Still got some choice. R and S can still arbitrarily just multiply to give me this quantity. The easiest way to ensure this holds is to let R be 1 over B squared and S be that. So that R depends only on A over B and S depends only on C over D. As we are claiming there's a relationship, amazing sort of guess or something, that the radius depends on the denominator of the number. 1 over 2b squared. Oh, that's much easier then. That says for each fraction I just have to draw a circle where this rule tells me how big to make the circle. It's much easier because I only have to think about the point A over B and draw a circle at A over B of radius 1 over 2b squared. For various values of A and B, maybe that works. Then they'll all be tangent to each other. Choose an diameter, reciprocal of the square denominator. Maybe half of that or something. Oh, choosing just a diameter to 2r, fine, okay. It's consistent with how I chose the initial large circles, fine, because whatever we did at the start. And when we build the Fairy diagram inductively, each new vertex is the centre of a circle with the diameter 1 over b plus d squared, tangent to each of the 2 circles that we already had. A tangent x-axis. Because when we put in the median, it has AD minus BC. It's 1, and then so this will carry on being true? I don't quite get it. Why will this carry on being true as we do the median thing? Probably because of this sort of fact. So you put in this point and you make the radius, you make sure that thing has the right diameter, and then you're good. Seems a bit good, doesn't it? So just you put in the new point, and we're kind of choosing our new point to make sure that I say thinking about this circle and A over B, we're making sure that this quantity upstairs, which annoyingly also uses C's and D's, but never mind, is 1, and this product down here, B plus D. So kind of the new relationship between the new point and A over B. I want to check that those circles are tangent when I draw in this new one of diameter 1 over B plus D squared. So I should check that. Yeah, I haven't understood why this holds. No, okay, well I can sort of follow through the factors of 2 in my head and the B squared and the D squared. Oh right, okay, so the new one has got smaller, it's got a larger denominator, so there's a bigger number here, but that's corresponded exactly by saying, okay, make sure it's got larger, make sure it's got smaller radius to balance exactly this sort of term on the left. And if it also has BC minus AD, then that is the correct simplification for your new pair of points. So I move to new points, so I keep A over B, and like new C over D, where C and D are calculated, C and D, the new ones are calculated like this, and I want to make sure that that one also does it. Well, good news, good news, it's still true that this thing, I've constructed it carefully, is still equal to plus or minus 1, so I can still check the substitution. So I just need 1 over, and then new denominator to be 4. And then I suppose there's a new radius S. So this has radius R, and this has radius new S. Previously S for the C over D circle, new S. And this like width radius. So there's kind of 3 numbers going on around here, never mind. And that's just fine so long as I keep the same relationship. So this R is taking care of this 1 over B, and this S tilde needs to be in the same sort of relationship with D tilde, and then it's all fine. So this tells me I can draw 4 circles without thinking about pairs of points. They'll just magically turn out to be tangent because the maths checks out. Let's read the maths. So it's a pretty sensible diagram on the previous page to do with these 2 circles. They're tangent, you can see that from the picture because there's this point of tangency, and they have radius R and radius S. So there's all sorts of stuff going on that I'm just doing a great job drawing this picture, aren't I? There's R plus S on the hypotenuse, R minus S on this side, and this side is something confusing like C over D minus A over B. There we go. So then you get this kind of Pythagoras sort of thing going on in here. And then if you rearrange this, you get R squared and S squared on both sides. So you get 4RS. And then this thing over here involves something that looks a lot like the determinant of a 2x2 matrix, because we're still sort of thinking of these as 2x2. Anyway, never mind. BC minus AD over BD all squared. Good. Right, well, let's draw that instead. Whose diameter greater than the fixed number is not associated with fractions of various series, restricting attention. There was this orthogonal semicircle stuff, which was okay. I think we just have to go for all points. Oh no, I still need to check. No, it's fine. They'll just turn out to not be tangent, I think. Let's get a Desmos chart up. So I think this lets us just draw points. So we're kind of looking at points A, comma B for A in 1, like we had before. And I think this is going to solve for us the kind of tricky bit about keeping track of which things are supposed to be connected. It's just visually these circles are just going to turn out to be tangent by the maths that we were just looking at. Why is that cross with me? Oh, I haven't told it what Qmax is. It's not very fair, was it? No, it's not happy with that because I have to wrap everything in square brackets. It's still not happy with me. What's wrong with max? That's only letters. Fine, I'll call it Q. You're fine with it being Qmax in the previous example. Oh, maybe you're not happy with the word max. Oh, maybe it made the operator or something. Oh dear, maybe Keymax was wrong. Anyway, good. So I have this kind of pairs of points, but what do I actually want? I want a forward circle there. So a bit tricky. Here comes the forward circle. Hello, Soundview321. Welcome to Chill Math Stream. We're trying to draw loads of circles in Desmos. According to a particular rule, they're supposed to be forward circles. Forward circles have the following properties. Then the centre of the forward circle is somewhere on the x-axis at the fraction a over b. So currently you're looking at a grid of points, but I'm going to make some fractions for where the midpoint of the circle is. They're not. Sorry, the midpoint's not on the x-axis. The midpoint's not on the axis, so that's the kind of x location. That's the x-coordinate of the midpoint, which we're going to call m for our list of midpoints. And they have a particular radius, which is 1 over... So I need this same sort of formula, but the radius is 1 over 2b squared, which looks a bit mad. And doesn't involve a, but never mind. That's just fine. So then what I want to plot is something like, I said that was the x-coordinate, and then for the y-coordinate, I want them to be tangent to the x-axis. Those are parabolas. I want them to be tangent to the y-axis. So I'm going to do this. The y-coordinate, if the centre is r. So this is going to be a list of circles. There they are. There they are. Now some of mine are inside each other. Is that what I wanted? I have this diagram in the textbook. Oh, there's lots of tangent circles going on. That's quite good. I like that. I see. So I'm drawing lots of them at 1, I've noticed, where I've got kind of 2 over 4 and 1 over 2 going on at the same time. So I kind of want to restrict this list to points where GCD of A and B is 1. There we go. And now they've got the right denominator. So we're getting this nice bubble kind of structure of tangent circles, where magic of forward circles or something is that they're tangent to each other without me having to calculate which pairs are tangent to each other. Loads of pairs are tangent, which is something in a previous Desmos chart we had a second ago. Previous Desmos chart, we had this kind of issue with trying to draw all the tangencies. I should probably have done these in the same one because there's a nice relationship between these. Now this is going to be a slightly awkward thing where I try and copy them over. Yeah, let's try and copy this over because I think it's worth it. We've got not that. I've got too many tabs. I've got red circles, I've got green circles. I'd like to put both on the same picture, which involves copy pasting quite a bit of Desmos nonsense. I want all of the Desmos nonsense, please. R2, and then add this slider. And what's it supposed to be? 9. Let's go 8 or something to start off with. And then the circles, the green circles look like this. The green circles do have their centres on the x-axis. I regret this because it's thinking really hard. Okay, right, well, we'll just let that bake for a bit and see if it comes up with any circles. It's thinking. It's untitled. What's the worst that could happen? Good. Soundview is a Phobos Dream viewer. Hooray! Yeah, regret this. I'm going to try and abort this, I think. Just stop. Be one instead. Be happy. Be safe. Oh, it is not happy with me. Did not want me to copy paste those green circles. Hasn't even yet realised that they're circles. I may have ruined everything. Come back, all is forgiven. I'll go back to doing like this. There we go. I can put more bubbles in. That's good. Very nice. And I can make the numerators be 0, maybe? Oh, no, that's just some points. I'll put them in here. There we go. So I get that one in as well. Oh, this is very tame. Okay, good. So I can have all of my, circles. The dream is that I can just zoom and it will just do things. But notice how this is 100, This is 100, not 10,000. So I think Desmos can handle if we go a bit further. It's currently drawing loads over on the right. I don't care about points greater than 1. So let's put the other restriction that we've tried in, where they have to be like this. Okay, because now it's just going to draw this bit. Okay, and it's for filtering. It seems happy with me just filtering M rather than R, so I'm going to leave that for now. And try and do a bit more of a zoom. So we've got these circles. And currently it's going to a depth of about 10. I reckon I can push this to 100. I'm going to try 20. That's more like it. That's more like it. Maybe this is my dream, that now I have some non-trivial amount of zooming that I can do to reveal to you more circles that are stacked inside and all of them are tangent. And there's a hierarchy going on. Yeah, this is my preferred way of doing this. So instead of drawing one big semicircle at the start, I've got a story about 2 large circles. And then the median in between is the point where you can place a circle. The point where you can place a circle to be tangent to those 2. And apparently setting the radius to exactly this quantity to do with the denominator gets the thing just right. Okay, right, we're going to make some improvements. This is good, but not perfect. So first off, can I push this to like 80 or something mad? Will it complain? Not that cross with me. And now it's really non-trivial zoom, right? Oh, it's unhappy when I zoom. Some of those circles are not very round. Oh, but then pop and then they're in. You start to see the bit where it's a shame, this long chain of circles. These are papas, aren't they? Oh, but they're only on the bottom. They're not the asymmetric top down. It is pretty. Right, okay. I think what I'd like to do is assign a colour based on the denominator. I think. For the link to the size of the circle. This has gone a little bit laggy at 80, so just while I'm messing around with it, I'm going to go back to 50, which seems pretty happy with me. Yeah, it's quite responsive at the moment. And I can zoom a bit. Not all the way, because never going to get all the way. So firstly, I think this would be nicer, oops, slightly losing it, if they were filled in. Oh, and then Desmos died. No, there we go, okay. So filled in I think is nice, not certain, but the thing I really want to change is the kind of red. How do I do this? I used to know there's some sort of way, right, where you can edit the colour. I know Math222, if they're still in chat, knows how to do colour in Desmos. Let me look it up. Custom colours, yes please. Help page, always look at the help pages. Defining a custom colour, yes please, right, okay. Hue, HSV, good, okay. Fine, looks good. I'd like it to be HSVE, I think. Then they'll show up in the colour. Oh, then they'll show up in the colour picker. Right. Okay. Yeah. Okay. So, but I sort of want this to be a function. So, can I have a variable in it? Maybe. Maybe I can. Maybe I'll have f of x. This is daft, but let's just see if it does it like this. Hue. What's a sensible value for S? 0.7 and 0.65? Okay, that's not really worked, has it? Let's go 1 or something. Oh, why is it still unhappy? Let's assign it to a variable. Okay. Okay, but I was kind of hoping that it would let me change this to sort of... Are you with my lists? Wait, what? I'm being daft. Why are these? Come on, let me have it as linked to a variable. List of colours, yes. I kind of just want to define it as like in I want to delay this value to depend on B. Oh, I can just put in. Oh, right, so just put it in a list, right? Like one of these lists. like the colours of these things. It's going to be in the same way that for the forward circles, the radius is just determined by B. Maybe I just stick B in here. B is going as high as Q, so let's do this times like 5 or something. 10 maybe. And then I just need to put in like my logic so that I have a colour for each circle. Maybe? Okay, there's some like list of colours. And I already hate this. I want to just max it out. Yeah, really bright colours, great. And then maybe this list of circles, maybe I can just put the colour in like this, and it will just colour them all in the correct colours. Yes, maybe it will. Good. Maybe it will. Look, colour depending on the radius. Smaller circles, different colour. There we go. RFL, that's what we wanted. Different circles, different colours. Okay. Nice. I think it's much slower at drawing them with the colouring in. So maybe I'll go back to this. And ooh, that's quite weird. Up the thickness of the lines. I always forget that I can. I think this is not a great effect going on. This is very jarring now, so now I want to turn it down, you see. Give me a slider. This is asking quite a lot of Desmos now. So I'd like it to just redraw until I'm happy with the colours. Oh, I see, so that's saturation. I do like saturation, but maybe it's V. What does V even stand for in HSV? Value. How bright? Okay, so brightness is the thing that's currently a bit sickening. I can have lots of that, but maybe not so much of that. That was briefly 0. Oh, okay, but 0.6 is a bit underkill. 0.8. Yeah, that's a bit less sickening. Oh, Math222 has a version. T button's not working. We've hit 3 o'clock. It's tea time. Tea time. So maybe I bring the brightness down a little bit to make it less primary coloured. A bit greyer, a bit grungy. Go back to colouring in the circles. Grunge. Okay, it's going through the colours too quickly, so that's this parameter, isn't it? Where I had 10 times B. I'd like to consider 5 times B. So they go sort of, okay, briefly just the number 5. Red, orange, yellow, green, and then kind of as B goes through different fractions, different numbers. We've got this enormous red circle out here. That's not a disaster. Ooh, up as new T. Right, okay, let me fiddle with some settings. Viewer rewards, channel points, enable channel points. Oh, they're called 0-dimensional points. I forgot we did that. There's a T time reward, which I'm halving and redeeming. Can I redeem it? Hey, I bet I can. Oh no, maybe I can't. Maybe I can't. Oh, I can review requests. Oh, fun. I'm supposed to be reviewing these, am I? 6 months ago, Charlie told me to drink water. I wonder if you get a notification if I now approve that. 4 months ago, Maths told me to drink tea. Laz Joma told me to drink some tea 4 months ago. Murray told me to drink tea basically every week for the last many live streams. Yeah. Oh, I turned it down. I turned it down. I thought that'd be good. I thought that might make someone redeem it. Still gotta claim it. Still gotta claw in the channel points to stop people accumulating too many of them. Let's look at the Math222 version. Yeah. Ah, right. Okay, you've done it iteratively. Okay. Yeah, you know about things like join. You need now to know. Oh my goodness. Okay. You've given it a starting list of numbers in the Fourier sequence. And what are these? Who knows what these are? And it's joining. Oh my goodness. It's doing some median stuff, maybe? No, I'm not sure what this is doing. Maybe it's median. Oh yeah, so you're doing a big filtering exercise on this, maybe, or something. I don't know. What do? I iterate. Oh, so I can keep iterating and it will keep doing the. So if this is a version where if I zoom in, then can I just have the sorry, can I just have positive? But if I want more, then I can keep iterating. Until I hit the 10,000 element limit. Okay, so Math222 version does draw in lots of circles, but has this kind of same. So this is when we were doing the first version, right? It has this kind of issue that it's doing these very slowly. There's numbers in here that have quite reasonable denominators. It seems like a big gap. Oh, so if you reset, you can see each time. Oh, I see. It was not fully reset when I started. So first one draws that circle, and then I see. So you can draw in this median, and then draw in the medians of the medians, and then put the next line. Oh, very good. You've got it. Doing the two things each time. Drawing in the kind of M shape in between, using the median each time. Very nice. And then it's given up at that point, which is strange, right? It's really annoying in a way because I don't think there are 10,000 semicircles on the board. Along the way, we've calculated about 10,000 things, so Desmos has kind of given up because it's too many things. But I really don't think we've got 10,000 semicircles. Whereas with the Ford circles approach, it feels a bit more like the limit is. We've got this GCD thing in here, and we've got some irritating filtering out about half of them. But I think I'm currently asking Desmos to draw a couple of thousand circles. I suppose, yeah, it's unlikely that GCDs would have to both be even. That happens about a quarter of the time. Other numbers are available. Mumble, several thousand circles, I think, which I quite like because it feels a bit more like it's filling up space. I'm on the fence about whether I want this kind of, let's go 6 or something. I'm on the fence about whether I want this to be coloured in circles or not. Just having colour is nice, right, compared to the textbook. It's before the determinant rule. There you go. Oh, didn't hear a sound. I don't know if you heard that at home, but Mario's redeemed. Tea time! So it's the point of the stream where we briefly pause. It did work, got it working. Worth getting it working. At the point of the stream where we briefly pause, you maybe get to see an advert. Mark is complete. RFL. You maybe get to see an advert and you maybe go and quickly make a cup of tea. I'll be back in a couple of minutes, as long as it takes my kettle to boil, to get more tea. And then I think we're good. I think we're good on Ford circles. I think it's time to press on to new content. Which, goodness knows, it's taking long enough to read this book. We're now into February and almost out of chapter 2. So at this rate, well, we're going to slow down, aren't we? But hey, tea time. Right, back in a second with tea. See you then. Stream manager. Run our break. Go. Welcome back. I'm pretty sure the ad's finished. Have I remembered to unmute? Yes, we're back. Go eat a phone. Are we keeping it nice and being polite in chat? Oh yeah, it's about adverts. Harry at what uni? Captain America and being a teacher. Yeah, cool. Right, welcome back. Oh yeah, here we are. By the way, during the ad breaks, the stream just sort of carries on. That's the nice thing about having lots of people in the same place. It doesn't all need to be me talking, although here I am again. Haha, right. Here's a step question for Charlie. Oh, surprise, step stream. It's very related to what we were doing. I think we had it on screen last week. Oh, thanks, Paint. It's got two scroll levels. Neither of them are good. There we go. Step stream. Related to what we were up to, because it's about rational points and fractions. Hooray. I think last time we thought about this, or what would happen if you expanded this out, because of cos squared plus sine squared stuff, and sine squared plus cos squared stuff, and other terms going away, we think you get m plus 1. So if you set m to be the number 1, you get a rational point that's not got integers in it. It's a pretty low bar, isn't it? Wait, oh, on the circle x squared plus y squared equals 2. And this corresponds to a rotation or something, maybe. Who knows? Who knows? But the second half is the bit that I've been thinking about recently. In that, well, we read it and then it was hovering around at the back of my head for a while. How are you supposed to get from the circle x squared plus y squared equals 3 to the circle x squared plus y squared equals 11? And this part of the question has introduced some new stuff, like an integer 2 rational point, where these things are all whole numbers, and a non-integer 2 rational points, so many words, if none of them are integers. But maybe they could be, right, they have to be rational numbers, but maybe they're not integers. I don't think any of this is easy. So an integer 2 rational point is something like 1 plus root 2, 1 minus root 2. Does that work? When you square them, you get 1 squared, you get 1 squared and root 2 squared. Something. Oh yeah, so maybe I want, yes, maybe 1 squared plus root 2 squared would be the point with coordinates 1 comma root 2, which is of the form 1 0 0 1 for those 4 numbers. Those are rational. They're actually all integers, so that's an integer 2 rational point. And then I'm supposed to obtain a non-integer 2 rational point, for which I'm really hoping that this idea up here works, because I like reusing ideas. So I set m equals 2, sort of hoping this will be alright. Can I get this in a format where I can write on it? That's a bit of effort, isn't it? I'm almost done. Not even sure if Charlie's here. Wanted step stream in June though, and it's only February. Not quite what they requested. Yes, these last 2 points I think are the fun ones, where you've got to find things that are not all integers for those 4 letters, and yet they have to satisfy these equations. And I think I can do this one, but only by guessing, which annoys me, that I can find some points that, you know, if I assume that P and R are equal, Q and S are almost equal, I can guess some values that work. But that annoys me. There should probably be some sort of method for generating these. I don't really know what's going on here. I mean, it's a radical extension of the rationals that's going to give us some solutions to pretty simple looking equations. It's got a classic twist at the end, by the way, where there's a minus sign instead of a plus sign. So anything you were previously doing with cos and sine should now be cos and sine. Anyway, I'm not sure I've solved this in entirety, because I think there's quite a lot going on. I think I can do both parts now, but I had to think about it for ages. And this seems like the sort of question that I'm going to keep in the back of my head for finding points on this circle of maybe not just rational points, but maybe rational points augmented with rational multiples of root 2. Keep this question at the back of my head because this sort of thing feels related, like it might turn up again. It's probably inspired by a similar sort of maths that we might be about to bump into. That was Stepstream. Thank you for watching. Back to chill maths. There we go. Keeping it calm. With tea. Right. Everyone tunes out. Just here for the step question. I need to set up that transition properly to actually like change between things. Right, okay, we've got Desmos, Desmos, Desmos. Information about Desmos, more Desmos. I would like notes back. Oh, it's no longer active because we didn't look at it. Let's switch it back on. Is this going to be in the right place when it comes back? Technical issues. Please hold. It was not in the right place when it came back. Right, okay. I don't think I can read it at that size, so we're gonna, there we go. Oh, the joy of trying to configure stuff live. There we go. Okay, we're back. Back in chill maths. Back trying to learn about circles. Okay, and there's that thing about orthogonal things, orthogonal circles, which we did some maths over here that convinced us that it was all the same thing. Yeah, you get equal radius in here because of shared tangents from a point to this circle. So these two are the same length, and then crucially those two are the same length. So if you find the actual midpoint, that's the center of a semicircle that goes through all three. Do I believe that? No, so if you intersect, so if you join the centers, oh gosh, if you do something with the centers, what are these grey lines? Which ones do you draw first? So you have the two big circles. You draw in the tangent here, and now you have loads of pairs of tangents, which, by maths, have to be equal in length, and therefore that's the midpoint of this line segment. So you don't start by drawing in the midpoint, you start by drawing in this tangent, and aha, you demonstrate that it goes through the midpoint of A to B, and therefore it's the midpoint of the diameter, it's the centre of this semicircle that goes through all 3 points. Okay, good. Right, we're going to go back into chapter 2, where I think I have about 1 hour of stuff I think I've seen before, but it's good for me. It's like eating your greens to just sort of see things you think you've seen before. It'd be much easier to just skip it, but I think it's going to be good for us, at least good for me. So there's this calculation stuff that we looked at very quickly, but I think this is foreshadowing, it's sort of setting up for later on. For example, there's Lagrange's theorem, which we're not going to prove until section 4 or 5 or something. What do they say? Down here, in chapters 4 and 5, develop some theory, and then prove it in sections 4 and 5. And apparently it's going to be efficient, which I always like. Okay, then there's some facts about these convergent fractions. I think this is where we left things, because there's the bookmark. I think we're now going to get some stuff. Ah, good. And we've revised Ford circles at just the right moment. Well done us. Oh no, that 1 over 2b squared. That's highly relevant now. That's mad. It's going to come back. We've seen this as 1 over q squared. That's actually bonkers. I've just seen what's going to happen. Okay, here we go. Clear that star, because we've read it now. Information about how well an irrational number is approximated by the convergence in its continued fraction can be deduced from the geometry of Ford circles, those things that we just drew in rainbow colours in Desmos, which were introduced at the end of chapter 1. Here is one general statement we made. Each convergent P over Q, those are the numbers in a kind of zigzag bouncing path, pinball path it was called at one point, coming in towards an irrational number x, is within, and the good news is within 1 over q squared of x, like this. For example, if a convergent has a denominator 100 or greater, then convergent approximates x within amazing 1 over 10 to the 4. So it might. This is actually why I tried to make this visualization of the continued fraction for root 2. So I've got these convergents, these things that get closer and closer towards root 2 that you make from the continued fraction by truncating after a certain amount of time. Actually, this is 1 plus root 2, but whatever. And I thought this would show the kind of bouncing backwards and forwards, but it's actually quite hard to see the bouncing backwards and forwards because it's landing so near that you can't really, you have to zoom in to see the bouncing because it's so good. It's landing so near. This one is within 1 over q squared, where q is the denominator. Okay, back in. All right, this 1 over q squared is to do with the denominator of the fraction, and it is the same squared that appears in the Ford circle geometry, isn't it? Here we go, here's the geometry. To justify this estimate, suppose the convergent P over Q is connected to the next one, R over S, by an edge of that zigzag pinball path. Then we have, right, okay, so this is this one, and that's the next one. And we know that X is somewhere in between, because these things go backwards and forwards, left and right. Because they're medians, they're formed by taking the median a certain number of times, which bounds it to be somewhere in the segment. Anyway, so we're at P over Q. We're considering the next convergent, which would be R over S. Then we have S greater than or equal to Q. So the Ford circle at P over Q, this large one in this picture, which has diameter 1 over Q squared, is at least as large as the Ford circle over there, because we're going to get a larger denominator by doing the median rule. Larger denominator means smaller circle in our rainbow picture. At least as large as the Ford circle. Yep, okay. The number x lies between, so its distance to P over Q is less than twice the radius. I'm going to need that broken down, sorry. Less than twice the radius. So twice the radius. What's the radius got to do with the distance to x? T. Less than twice the radius. It's a triangle inequality thing and I can't see the triangle. I'm being silly. Where is this circle? Where's this triangle? Where is this? Less than twice. And that's going to be, then we're going to be done because we know how large the Ford circle is. Less than twice. So there's no less than twice. Oh, because this distance from P over Q to R over S, this distance is also less than twice the radius, because it would be twice the radius to get to somewhere over here, where here we go, where if the two circles were the same size, then the distance from their points of tangency would be twice the radius of one of those circles. But in fact, this one's smaller, which means it's closer. Can I do that with maths, please? So that feels like a kind of geometry, kind of intuitive thing that's replacing some maths, like some rule about how far away that is. I suppose we know a rule for how far away that is. We know what P over Q is, don't we? Oh no, but we know some relationship between these circles because we know that these things are, the rule that we had before was something like this. This thing squared is 4 times, then, I don't know, but we know these radiuses. We know the radiuses. This is going to be a tautology if I write it out like this. Right, we know this has a larger denominator, so smaller radius, but then I kind of want to relate the radiuses. Yeah, okay, so there's this line that comes down here. That's the length of the sum of the radiuses. Radii. Some of the radii down here. You have like R1. We're using R. We're using the letter R. Annoying. R1, R2 for the radiuses. And then that's at an angle, so the actual distance from P over Q to R over S is less than that. Still feels like we can do better because we know all the radiuses. We know what's going on. We know what these numbers are. I like the idea that we're bounding the distance to x by bounding it by the distance to the next one, which is something to do with the radii. I think we could do slightly better, can't we? Yeah, so there's some sort of dot product here. But no, because we can actually calculate this, right? The distance is just... well, we can just write it down. It's this, which is something like plus or minus 1 over QS. Because we know that they're consecutive terms. Connected, they're tangent circles, or if you like, there's a connection in the Ferri diagram from doing repeated median process stuff. So we know that determines plus or minus 1. And then I suppose I want the absolute value of that distance to get rid of the plus or minus 1, and also because distances. So all I want to say is that the claim here really, at its heart, the distance is this. We have this distance, which is 1 over QS or something, mod signs, sure. And the claim is that this is small. It's not as large as 1 over Q squared. And that's easy to prove. That is just saying that S is larger than Q, which is true. And I think that's more obvious if you write it out with a little line of algebra. But yeah, that distance is 1 over mod QS between the two. And that really is less than 1 over Q squared if S is. So proof is just that S is greater than Q. But by the way that we build this median from, build this conversion from the previous one, it's just got a larger denominator. Our median rule keeps adding things with positive denominator. Okay, cool, right. I believe it anyway. So this is good news. This means that your distance from P over Q to X is less than that. Less than 1 over Q squared. Wait, what? At least 1 out of every 2 is even closer than a factor of 2. Excuse me. What? Oh no, and now we're going to look at the previous figure. So now it feels like geometry. Here we go. It's the point in the projection of the interior of CP over Q to the x-axis. Oh, right, okay, similar for R over S and CR over S. Let's draw in that projection, which I believe is kind of... Oh, okay, so this could be on the left or the right, is that what they're saying? X is not actually underneath the point of tangency. X is an irrational number somewhere. So if it's if it's to the left of that line, then it's within the radius factor of 2. If it's on the right, then it's going to be within the radius of the next one. Okay. Every 2 successive convergence. Yeah, okay, left or right of the line. Okay, good. At least one of those 2 projections. Yeah, okay, not that. Right, good. Okay. What if every successive pair, one of them's actually really good. Do I care about the factor of 2? Not sure, not sure. And then here's a much better fact. Oh no, is this going to be because of the finitely many... The difference between a rational and an irrational number in this world, where we draw in these circles, is to do with having an infinite or finite number of circles passing over? Is it going to be something like that? Okay, here we go. Very strong optimality statement. If P over Q is a convergent in the continued fraction of x, then no rational number with denominator less than or equal to q is close to x is the best out of all of the numbers with that sort of denominator. So when you hear that 355 over 113 is a really good approximation to pi, people mean that even if you make the denominator, smaller than 113, you can't possibly do better. And also that it's within 1 over 113 squared of pi, which is pretty good. If I just guess my favourite denominator, then it's hard to get very close to pi. Right, consider two consecutive convergents. As before, and let T over U be any rational number with U less than or equal to Q. So this circle is at least as large. The circle is either disjoint from or tangent to C pi over Q and C over R over S. Maybe tangent to one of them or tangent to the other. Not both, because then it would have to be in between, and there's no room to fit the large circle there. Topology! Here we go! That feels like, I don't know if that's really topology, but that feels like a very kind of, you can't fit a big circle in there. That's excellent. One's corresponding to, so if this is like pi or something in here for the number x, and we're doing quite well with these approximations in our kind of zigzag pinball path in towards pi, then a fraction with a smaller denominator would have a larger forward circle. So it would have to be miles away in order to fit in this picture, where the circles don't overlap. The circles are just tangent to some of the other circles, or completely miles away. So if this is 22 over 7, and that's the next one, and you think, well, pi is actually quite well approximated by 16 over 5, and 5 is a small number. Well, 16 over 5 is kind of fairly nearby, but over 5 means that it's associated with a massive forward circle, which so must be looming off to the right somewhere. Also, 16 over 5 is 3.2, it's not even that good. So it might be tangent to some of these circles, but it might not. And now they're going to tell me that it's very far away. Could it be on the other side to P over Q? Okay, is it right? There we go. If it's on the opposite side, then T of U would be farther from X than P over Q is. So T of U would not be a close approximation. It's on the opposite side of P over Q from R over S. Oh, like if it's miles away, then it's terrible. The remaining possibility is that T of U is on the opposite side of R over S from P over Q. What? So this sentence says if T over U is on the opposite side of P over Q from R over S, and then this one says it's on the opposite side of R over S from P over Q. I sort of get why these framesters. Neither of those is a phrase that's on the same side as, because we're trying to explain that the circle is diametrically opposed, one way around or the other. Goodness me. Okay, I need a picture, right? So we've got this P over Q circle, and we've got in our diagram an R over S circle for the next one, and we're imagining this kind of circle that corresponds to an approximate contender to the throne could do a better job of P over Q at approximating X, which means it has to be closer to X, and that's pretty hard for it to do because it's associated with a massive forward circle. P over Q is a little bit further away from X, possibly than R over S is, so there's this kind of outside chance that the big circle is sort of somehow really close in here on this side, perfect circle every time. So this like perfect large circle. It's an impossible circle to draw, so I have an argument, right? I have to draw a very large circle that's somehow very close, even though there's this circle in the middle in the way, and that over here is the case that we're about to consider. Let C be any circle in the upper half plane with the same geometric properties as C to T over U. Goodness me. Okay. Oh, look, here's a picture. Always draw your own picture, just in case. Just a scroll away, amazing stuff. Right. C be any circle in the upper half plane. It seems like a hard task to prove this. So I'm just going to read, I think. same geometric properties as TV. Namely, C is tangent to the x-axis at some point on the opposite side of R over S from P over Q. So over here somewhere, it's trying to be really close to X, closer than P over Q, even though it's a larger circle. And there's this R over S circle in the way. C is either like this, or disjoint, or like that. We wish to show that Z is further away from X than P over Q is. Sliding C along the axis further is bad, so assume it touches either one or the other. Increasing the size of C while giving it tangent to CP of Q. What's the ROS? Also moves Z further away. This is another intuitive geometry sort of thing, but also I believe this one. So we may assume that C has the same size as CP over Q. Yeah, okay. It's then evident that Z is further from X than P over Q is, finishing under. Oh, I don't like this. Okay, not very satisfied by that argument. Big circles have to be far away, is essentially the argument. But there's some stuff about how you do that. We just have the large circle was kind of. There's a fact that we did with some algebra underneath. So in this case, where you've got your next approximation, your next convergent to the number x is pretty tiny, and you sort of just somewhere down here. It's really not obvious to me that this one is further away from x than it is from that. Than x is from that, sorry. I suppose this point is to the left of this point. Oh, that's not even, because this could be even larger, right? So this could 10 point tangent could be on the right of that one. That's not even true. Not even true. Oh, it's just going to be that. So in this case, if you bring down the size of this circle until it's the same as the left one, then you have a nice symmetric picture with this kind of circle just splitting it off to say x is somewhere on the left, because down the middle of the picture, you can't have this circle being tangent to the left circle while itself being somewhere on the right. I mean, yeah, you can, but yeah, you can. I think loads of things are possible. This is not obvious to me yet. It's a shame. It feels like this kind of like intuitive big circle idea is really good, and for the author and possibly every other reader, it's just really obvious why. Or just clear from this. Once they have the same size, what's going on? The small circle in between kind of splits off x to being, actually it prefers to be on this side near P over Q than this pretender Z point. Which kind of works, I think. I can sort of see what they're trying to do. I'm just not really convinced it always happens. I mean, they say it does, and I sort of trust them, but I'm worried about having a diagram like this, but with R over S further right, and this circle still being like comes round to the left, and it's still tangent to this circle on the left. It's not obvious to me why that can't happen. Yeah, okay, it's becoming more obvious. So if these two are the same size, I sort of accept that I should consider these cases where the circle C is the same size. Do I though? Because there's some complicated relationship between, you can't just slide it, it's whole numbers. I'm supposed to believe that these circles never overlap, I think. I might have proved that in a page that I skipped or something. Yeah, okay, I'm going to put a star here as a thing to come back to, but I think we're moving on. Hello. Okay. The last fact we would deduce from the diagram is the convergence converge monotonically. Note the convergence to the left of x is getting steadily close to x. The same is true for the convergence on the right. And in fact, each one is closer to x than the one before. Oh, by considering the next one. Okay. Consider the next one. The circle is tangent to these ones minus tangent to those ones. One of the other forward circles tangent to C over S farther from C P over Q. Point x lies between them. So consider the case that it was actually tangent to P over Q as well. And T over U is the median of those. So we saw if it's closer to R of S than P over Q. Possibly equidistance if it's all in the middle. Okay, this feels more like more effort to prove that this thing is closer to one side. Which is fair enough then. That the if you do 2 steps, then you more than halve this distance. That seems reasonable actually. Better than half it. Make it really small. This distance, sorry, from fraction to x. So by factor 1, 2. Don't know. Don't know. I thought I was going to enjoy this forward circle stuff, and I've realised that I want to see some proofs of forward circle things. I'm just going to go and quickly look at. Ask permission, I suppose. Can I go and look at section 1.2 to try and find out this fact? T over U is closer to R over S than P over Q because it's the median. Feels like the sort of thing I should prove, to be honest. Let's go and look at section 1.2 because it might be faster. Page 61 when we come back. Where are we? I've jumped. Oh no, terrible. Jumped to completely the wrong place. Thanks, Mary. Section 1.1. Section 1.2 has a very series stuff. And okay, so section 1.2. This is more stuff I skipped, isn't it? This version of the diagram. It puts all of these in as well. But that's because I wasn't super excited. Oh hey, up. What's this? Oh no. I just want to see the maths, right? I just want to see the maths that tells me it's closer. Yeah, right, good. From the geometric interpretation, no! The median of these two fractions. No, I don't want to do this by geometric intuition. I was hoping it would be numbers. Oh dear. Okay, I mean, fair enough, look. In this interpretation of the diagram, you can move this point and it moves in that direction, so it's all okay. We just calculate, right? It won't be as maybe geometrically illuminating, but if you have the median A to C and you find the difference to A over B. On one hand, this is it's actually something really nice, right? So this is AB, or I shouldn't point with my fingers. AB plus CB minus AB plus AD. So this is going to cancel nicely. AB, CB, take away the AB. So CB minus AD. Oh, it's everybody's favourite expression. Plus or minus 1. A for B, B plus D. Versus if you do the same thing but finding the different distance to B over D, then you get this rule is sum of the denominators and other denominator. So the relationship here is just if you want a small distance, it's whichever of B or D was the larger, the one with the larger denominator, the median is closer to the one with the larger denominator, just because you can calculate those distances. And then, I mean, even if you don't believe me that this is plus or minus 1 upstairs, it's the same quantity upstairs. AD minus BC, up to plus or minuses. Obviously, I should probably have flipped the distance of one of these because I'm doing x minus a and x minus. Plus or minus signs. Put mod signs everywhere if you like. Same numerator, different denominators, b or d in, depending on whether I'm looking at the distances. That's the maths I thought I was going to see. Fine, you can do it geometrically with squares in a different way of building the thing. Fine, okay. Why are you reading a topology book if you hate geometric reasoning? Sort of also hoping that, sort of hoping to see both. Oh, I don't know. Okay. Right, good. That was some stuff about how good approximations are, which I think I'm sort of a bit sold. It's a fact I've heard before that the convergents are within 1 over q squared, and that they're the best you can do. I'm not totally sold on this geometric proof, but I could imagine sort of convincing myself by moving some circles around that it was always true. Okay, right, more greens. I thought we would get Chinese remainder theorem or something, but we're getting more fun facts, which is good. Okay, doubly infinite. This is going to go from one place to another. Infinitely far at both ends. Yes, okay, here we go. Like this, maybe. Where these numbers could be anything, I think. There's not necessarily any sequence to these. Okay, good. Let L be a line running down the middle of the strip from end to end. L. Viewing L as a path in the half plane model, L cannot cross only vertical edges. Right, okay, because then they would all be coming from the same direction. So some semicircles crossing in the downward direction into the adjacent triangle. The next edge that L crosses will be one of the other 2 shorter semicircular edges of this triangle. Okay, sure. The semicircles cross to becoming smaller and smaller with the diameters approaching 0, as we saw in our. Okay, you have to keep crossing these. You have to keep crossing these medians. When you enter a triangle, you can't double back. This is topology, maybe. You can't double back and cross the same line. Again, you're crossing different lines on the way in. So this line that crosses infinitely many of these semicircles has to end up at alpha on one side and beta on the other. It's kind of forced to be. If you chop it off, it's forced to be some continued fraction for something. It's going to converge to some beta. That's quite mad. Okay, I like that. Or possibly going to a completely different number. What's this say? Unique limiting point lies between the 2 endpoints. Good. And so this doubly infinite thing has to keep crossing lines. So it has to keep doing the thing that a continued fraction would do. So it had to be a continued fraction in some sense. Okay, so we're crossing the upper semicircular edge of a triangle T with the strip of the figure on the left below. Okay. What is all this? Turning and crossing the other smaller semicircular edge of T in the downward direction. And we'll then continue downward forever. Yep, good, okay. Not a vertex of the strip in this case, okay. But then it stays in the strip forever as we move upwards, so eventually it lies in a triangle T alpha. It gets high enough. And now it's going to have to cross a vertical line. Right or left across a finite number of other triangles having 1 over 0 as a vertex, the vertical lines. Before turning downwards to cross, again, then it goes in towards something else. Okay. One conclusion we can draw from this analysis of the infinite strip is that its endpoints alpha and beta cannot be the same number. Yeah, all right. First figure, alpha and beta lie below the 2 different lower edges of the triangle T. Yeah, okay, you at some point would have to turn around and go back down the same path or something like that. Yeah, okay. And these are just completely different numbers that differ by, they're not. I have the floor of these numbers is different integers, so they're just different. Okay. Denominators y approaching infinity at the ends of the strip, and numerators approaching x approaching either plus or minus infinity. You keep doing you keep doing this. So you're generating continued fraction for these things, right? There's a unique infinite strip. Okay. alpha and beta determine the vertical lines in the figures. Oh, right, yep. You draw a vertical line from that point upwards. Okay, you can make the continued fraction and glue them together or something. That's more to try and go with a fairy diagram whose projection of the x-axis includes both alpha and beta. Oh my goodness, right, textbook. What are we doing? Take all of the triangles in the fairy diagram, meet the semicircle in the upper half plane with endpoints alpha and beta. I should just draw a big semicircle. Draw a big semicircle and see what you get. Can cross an edge of the fairy diagram only once, since if two semicircles in the upper half plane with endpoints on the x-axis intersecting more than one point, they must coincide. Yeah, intuitively, you've got two semicircles. Where are you going to put them to intersect twice? Your semicircles. They could be the same, but you can't get them to intersect exactly twice without intersecting. Twice means they're the same. They can't be tangent unless the point of tangency is one of the endpoints. Often be irrational. Okay, good. It crosses the triangle from one edge to another edge. The semicircle cannot cross an infinite number of triangles having a common vertex. Otherwise, the semicircle would contain points arbitrarily close to the common vertex. Cannot be either of the irrational numbers. Okay. Right, okay. That is a nice way to make an infinite strip of triangles that goes from alpha to beta. Uniquely determined. So this applies to the semicircle from alpha to beta crosses exactly the same triangles as any line that went from alpha to beta would. Two vertical segments joined at the top by a 180-degree bend. This may seem odd at first glance, but what it means is that the height of the vertical segments cannot be too large compared to the distance between them. The construction of a strip connecting two irrational numbers via a semicircle with endpoints at n works equally well when alpha or beta is rational, but in this case the strip only has a finite number of triangles at the rational end. Very special case of when they are the endpoints of an edge of the fairy diagram, when the strip degenerates to just this edge, which is like almost the opposite of an infinite, doubly infinite strip. Okay, we're going to look at ones that are periodic along their whole length. Okay, here we go then. So this is the bit of, right, okay. So we're going to try and understand continued fractions with some periodicity to them. Oh, we've thought about reading forwards and backwards. Right, okay, spotting links, right? Last week we looked at a continued fraction and said, that's strange. It's got part of it's periodic. It repeats. It's periodic and it's the same forwards and backwards. It's a particular sort of continued fraction, which is going to be like a particular sort of doubly infinite strip. Because continued fractions and infinite strips are kind of the same. Well, the triangles that make up a strip, infinite or not, are kind of the same thing as the continued fraction. Right, try and hold all of that in your head all at the same time. Here we go. As we'll see, the irrational numbers alpha and beta end up being the two roots of a quadratic equation with integer coefficients. So if you care about the continued fraction of a quadratic equation with integer coefficients, maybe this is one of them. So like these ones, which have... oh no, this is not quite the same thing. So then if you want to make the continued fraction of something like that, where do you start? You start up at infinity and you come down. So it's going to be quite similar. Right. Okay. Almost 4 o'clock. Probably time to stop, to be honest. Interesting. There's some exercises to evaluate continued fractions, all of which have some periodicity to them. So to get accurate to 4 decimal places, I think you only need, well, if you get to a denominator of about 100, then you've done fine, because you're now within 1 over 10 to the 4. So that fact is that squaring factor that we've had before. We can kind of do it on the plot, right? There's a translation factor, root 5 minus 1. But if we go in the Ford circles picture and look at, is this going to work? I don't know. Look at this number. I think we can do the continued fraction for this blue point. Let's make it a little bit larger. I think we can do the continued fraction for this blue point just by counting circles. Oh, is that true? So we're going to count the circles on either side. I'm trying to follow a path, right? So trying to follow a path that goes from in here somewhere and comes down through here, and then count how many. Oh, is this how it works? You count how many? Something like this. So this is yeah. This is okay. So if I imagine this is more like, this has got some semicircles. You can't see them, but it's got some semicircles that come down to these points of tangencies, all the ones that are tangent to this huge red curve. And I have to count which turning I want to take. Don't miss your turning, don't miss the blue spot. But do you want the first one? So there's kind of this 0th one that goes up to 1, a semicircle that goes over here. But maybe I want this one instead, and then go and jump down here somewhere in these small forward circles. But no, I don't want that. I want to get to this one. So I want to do, that looks like 1, 2, 3 to me. What's the value of? Let's tell me the value. No. I think this is going to work. This is going to be a bit of a party trick, isn't it? If we can read off the continued fraction from this picture. I might be out by 1 for a lot of this, but I think it goes 0, 1, 2, 3. And then jump, and then go 1, 2, 3, and then jump in here. Oh no, then I'm out. But I think it might go 3, 3 or something, or possibly 4, 4 or 2, 2. Okay, what's actually the continued fraction of root 5 minus 2? So to calculate that, oh, bad news. I think it is more like 1/5, isn't it? Yeah, this is a disaster. Isn't the first thing 5? Because it's slightly more than 1/5. No, this is okay. It's like 1/4. So I think it might be 4, 4 is maybe the prediction I'm trying to make. Let's do the reciprocal of this. So root 5 is, okay, let's get a calculator time. So to calculate it, I'm going to do this. That's about 4. So my first approximation is 1/4, and I think my next approximation is that it's 1/4 plus 1/4. That's not bad, than an approximation to root 5 minus 2. I think I've got that right, but it's not this. It's more like this with a 5 there. It's not this. It's miles off. 4, 4. Okay, so my counting was out by 1. Possibly this one counts. Possibly I'm supposed to go 1, 2, 3, 4, and then go in, and go, oh, I missed this one. 1, 2, 3, 4, and then go in. Yeah, so count circles that are smaller or equal in size. Count circles that are smaller or equal in size, and take your turning, but don't go too far into the infinite vortex of tiny circles. So I think it's 1, 2, 3, 4. And then 1, 2, 3, 4, and then at least 1, 2. Oh, I can up this, can't I? Party trick, let's go. 1, 2, 3. Oh, I can't quite tell if I want another one. I think I don't want another one. So as this looks like 1, 2, 3, 4 again. Is the continued fraction of root 5 minus 2 just loads of 4s? Because that is ruining my party trick somewhat. Quick Google search. If it's always 4, I don't look like I'm calculating anything. I look like I'm just continuously saying 4. Root 5 minus 2. Continued, yeah, I want a continued fraction though. Yeah, it's just loads of 4s. Okay, thank you for seeing me calculate this with forward circles. The answer is 4 from the forward circles. Let's have a more fun one. So possibly this will be good. Yeah, okay, so this says, if I look at pi minus 3, then I should see 7 circles, don't miss your turning, and then 15 circles, don't miss your turning. Oh, that's going to be exciting, isn't it? So let's have a look. Not this. I'm bored of that. Let's go pi minus 3. I have to put in a number between 0 and 1 for this bit of experiment because I've limited my plot to being just the forward circles between 0 and 1. Okay, there's the number we're trying to approximate with convergence. And the way we're going to do that is we're going to count how many circles down this lovely picture we're going to use until we want to jump in the other direction. So starting from the left somewhere. So I go 1, 2, 3, 4, 5, 6, 7, but then I don't want to go to the 8th one because then I'll be down in this bit of tangent here. It's in the mess of circles that are tangents of this one and 7 down here. And then have I got enough circles in my picture? Because I want to go 1, 2, 3, 4, the blue one, 5, 6, 7, 8, 9, 10, 11, or something more than 11. Something more than 11, but only a bit more than 11. Can I just up this a little bit? Come on. Come on. Oh, it's not happy with me because the lists have got too long because we've done such clumsy Desmos stuff. Let's pull it back. Oh, I think it's only got me down to... Hasn't got me down to 15 of them. Right, cool. It's clearly more than 11. Good. Maybe I should do... Maybe more fun to do... a golden ratio or something, because that's got a pretty fun continued fraction. But I guess I should subtract 1 from it, so there's a number between 0 and 1. Oh, this is just the Fibonacci thing, which I've done to death, right? The Fibonacci thing. So this one is over here on the right somewhere, so that you take the first turning. You say, no, I want to go in this circle and look at things tangent to the other big red circle, and then I want to go into this first thing that's tangent to, and it's on there somewhere. I don't want to go down. Don't want to go down here. I want to go stay here, and then reading through these things that are tangent to that circle. How many of them do you want? Well, really just 1, and then I'll go in the next 1, and then I'll go in the next 1, and the next 1, and then this green one and this blue one, and just 1 each time gets me down towards something to do with the golden ratio. Just going 1 each time. Okay, I'm going to do 1 more where I don't know the answer. I can maybe guess the answer, but I'm going to try going 2 each time. So take this circle, 1, 2 for this one, reading round clockwise. Circles that tangent, 1, 2, and now with this circle, I'm going to read round smaller or equal circles that are tangent, going round anti-clockwise from the top, 1, 2. And then for this circle, I'm going to read round clockwise, I think. Yeah, 1, 2, so I go around here. So 1, 2, and then in here 1, 2, and then in here 1, 2, and I've ended up at 0.4142. So by doing 2 circles each time, I'm doing the continued fraction 1 over 2 plus 1 over 2 plus 1 over 2, and I've got down to root 2 minus 1, 0.4142. So there's this nice relationship between the number of turns or the number of tangent circles you look at and the number you end up at, which is continued fractions, but visualized here by zooming in to all of the circles. That briefly was a kind of vertical strip above, which is has been relevant at some point earlier. Good, right, okay. I think this picture is getting there. I would love to consider a kind of speed up where I could trick Desmos into only thinking about numbers, so that instead of going up to q squared here, which is 81,090, instead of going as high as q squared, actually q times q plus 1, instead of going as high as q squared, if I could trick it into doing some of this filtering beforehand to rule out, I guess maybe sort of quarter to a half of the points, I could get a few more circles in this picture. Actually thought, can you load in? So really what I want it to do is to redraw based on what's visible right now. So as I zoom in, it will redraw. Can I get like, does Desmos know a variable for left side of plot? Does Desmos know where the viewport is? Desmos get viewport? Yeah, can I get the size? Desmos doesn't know where it is. It knows the height and width. What, in pixels or something? It doesn't know these. Can you set these? Can you set these to variables? Can I make my own zoom? Maybe I can make my own zoom. It'll be really clunky, but maybe. Can I set these to be variables? Just like, probably not. No chance, right? You can just put like a K in here. Nah, I thought not. Yeah, it's not happy with that. Yeah, I want to be able to set the viewport. I don't want to use the plus and minus signs. Okay, another time I think is going to be. Oh my goodness, where's this trying to do? Found some mad Desmos stuff that's like jumping backwards and forwards. Okay, possibly a solved thing. Yeah, scale everything. Ooh, I like that. It would, yeah, okay, I like that. Because I like the depth of stuff that we've got here is good. I'd need to create my own x-axis, I think, would be a challenge. But not impossible to overcome that. Because like I'd like to, I don't know, maybe switch off their axis, x-axis, and have a secret scale factor that would, you know, switch off the grid and everything. And have a secret kind of some labelled points that are also being rescaled and cleverly redrawn or something. So yeah, fake x-axis. The zoom is going to be weird because I also need to pan around. I suppose I only need to pan left and right, which to be honest sounds like a slider, doesn't it? So yeah, I think cook. the thing to cook is like redo it so that we're controlling, yeah, zoom level as a variable, redraw everything scaled up, recalculate lots of fractions in the given range. And maybe I don't need so many fractions in the given range, right? Like currently I'm restricting it to things that are fractions that are between 0 and 1. I could do that on a smaller range because I'm only looking at 0.1 to 0.8 right now. Yeah, the trippy thing would be you could then have a scale. You could press play on the scale bar and it would just zoom. And if it were a periodic continued fraction, then it would be a looping GIF that you could do to show how you go in towards, like we just saw, there was some repeating pattern, loads of 4s for the one that was root 5 minus 2. So you could have it would center that point. Yeah, so yeah, you'd want a point which centers the kind of, what are you looking at? And it'll draw that in the middle. Do not move the graph around. And it'll draw that in the middle. So that's just this, isn't it? Oh, this is annoying me, but with its slowness. Maybe to be continued, but yeah, you kind of choose your target point and then scale everything. So like the K factor would be, so there'd be some shift for some kind of target point. So T is my target, which is root 5 minus 2 or something. So I've got my target point. Okay, so it's moved my target point to be at the origin. And then there's some scale factor, which goes here and here to scale the radius. And the plan is that at the moment it doesn't redraw, but as you move this slider, it'll make the fractions larger. Very janky at the moment. So this should start at 1 and go to 5 or something for a scale factor of 5, and it's not going to be able to redraw this fast enough, so we're going to turn that down for now so that as you zoom you can see the circles, and then don't come back down again. As you zoom, you can see the circles getting, you can see you're zooming in, and you can see this kind of sequence of 4 circles, but it should redraw more stuff. So these things should also vary depending on, the denominators should also vary. Oh gosh, the very fractions that we're considering should be fractions that are nearby. So you've got to parameterize those up to some limit of the scale stuff, but you got to choose some. That is tough. That's really tough because the fractions nearby could have weird denominators that are large numbers, or they could have small denominators. I guess after a while they won't have small denominators. We've seen that the things that are nearby are only the ones corresponding to small circles. But parameterizing which fractions you want is, that's not obvious. If you're not allowed to calculate all of them and restrict to the ones that are in the correct range, because that's what we're trying to avoid doing. We're trying to only generate fractions that are in the right range. And they could be like prime numerator and denominator that just happens to be in the right range. Yeah, I can't see it. I can't see how to do that at the moment. Okay. Future homework, I think. Right, save it for now. Good, right, that was the stream, I think. Thanks for watching Chill Maths, where we mess around with a textbook, continued fractions, geometry of the upper half plane, that sort of stuff. I think I am back next week. Watch me do it the other way around. Should really have prepared this. Yeah, pretty sure I'm here next week. So maybe we'll get the zooming thing working. Other streams are available, so if you like watching people do maths or CS stuff on Twitch, you can also follow nStucky and Phobosstream, who are both sub to this channel. Other people who are streamers who I've forgotten, I'm really sorry, but nStucky and Phobosstream I've seen around recently. You can follow them. They'll let us know in chat if they're streaming anytime soon. I can see Phobosstream's there. I'm doing my professional stream on Thursday, of course. I think I'm back next week. Have a good one, everyone. Take care, and see you around. Creating a manual x-axis is fun. We've got our own definition of fun in this Twitch channel. Right, good. Okay. Bye. I'm ending the live stream. That's what Irv taught me to say. I'm ending the live stream now.